Now we are going to discuss one important topic, which is the operating characteristics of DC generators. Okay. So what is meant by operating characteristics? It is the variation of one parameter with respect to another parameter. So what are these characteristics? The first one is the no load, or you can also call it as the open circuit characteristics. So we have discussed this for a self-excited generator, right? This is plotted between the internal generated voltage and the field current. So this resembles that of a BH curve, right? Now the next characteristic is called as the load characteristics. So here you are going to have again two characteristics. One is the internal characteristics and the other is the external characteristics. So what is this differentiation? The internal characteristic is the plot of the internal generated voltage versus the armature current or the load current. You can take either of them. And external characteristic is the terminal voltage versus the armature or load current. So in the first characteristic, there is no load connected. That's why it's called no load or open circuit characteristic. Second, it is called load characteristic because this is when the load is connected, what is the variation of these internal generated voltage and terminal voltages. Now if you talk about the no load or open circuit characteristic, like I discussed, it is similar to a BH curve, right? Resembles that of a BH curve. So irrespective of whether the generator is self-excited or separately excited or shunt, even in self-excited we have series, shunt or compound, right? In any of these generators, the curve is going to be just the same, which is the BH curve, okay? And it is also, you can say it is plotted for a particular speed, and as speed varies also we have seen what is the variation of the characteristic, okay? So if you have any doubt, you can refer back to the self-excited voltage buildup, okay? Now what about load characteristic? This is going to be different for each of the generators. So we are going to discuss with respect to each of the generator. First we will start with separately excited DC generator. So we know that the voltage, internal generated voltage, this is proportional to what? The field flux and the speed, okay? So for a particular speed, the generated voltage will depend on field flux, which for a separately excited generator is independent of the load current, right? So the generated voltage should be independent of the armature or load current. But again, what will come into picture? The armature reaction. Armature reaction will result in a demagnetizing effect, right? And it will depend on the armature current. So ideally, Eg should be constant with respect to the armature current. So this is the ideal characteristic. But in actuality, because of the armature reaction, there is going to be a slight droop as the current increases, okay? So this is the drop due to armature reaction. If it is given that there is no armature reaction or the armature reaction is ignored, negligible, then this is simply going to be the internal characteristic. Now what about the external characteristic? That is the terminal voltage Vt versus the armature current. Now what is Vt? This is equal to Eg minus IaRa. That means from the Eg, if you subtract the IaRa, then you're going to get the external characteristic, okay? So this in the graph you can draw like this. Now this is drop is due to armature winding, or you can write IaRa drop, okay? So what is this here? This is the internal characteristic and this is the external characteristic. And also the axis also, this is Eg and also Vt is also plotted with the same axis, okay? Let us now move on to the shunt DC generator, okay? So here what are the relations? The internal generated voltage, it is proportional to phi and omega. That is the flux, field flux and the speed of rotation. That is, anyways, it is same for separately excited as well. Now here the field flux is dependent on the field current, which is in turn equal to the terminal voltage divided by the shunt resistance, right? So that means this implies that the flux is proportional to the terminal voltage, okay? In separately excited case, flux was independent of the armature circuit, okay? So this is one relation. You can take this as first relation, this is second relation. And finally, what is Vt? The terminal voltage, you can write it as Eg minus Ia Ra, okay? Now using these three relations, we will get the characteristics, okay? So what will happen as the load increases? Load increases means the current that is derived by the load is increasing. This means that the armature current is rising, okay? Now what will happen when armature current rises? This is the only equation which has armature current, right? So as armature current rises, the drop across armature winding is going to increase. So the terminal voltage is going to decrease, okay? So here you can write this implies that the terminal voltage will fall, okay? Now once terminal voltage falls, then what is going to happen to the field flux? From equation 2 you can see that field flux will reduce, right? So you can write here field flux is going to reduce. If field flux reduces, then what is the resultant? The generated EMF is also going to reduce. So as load increases, the terminal voltage is reducing as well as the internal voltage, okay? This is one relationship. As Ia increases, Vt as well as Vg decreases. As Ia increases, Vt decreases as well as Eg decreases, okay? Another relation that you can see here is Vt is in turn dependent on the generated EMF as well. So what will happen when Eg reduces? Vt is going to further reduce. So this you can consider as a second relationship. As Vt decreases, Eg will decrease, which will further reduce the terminal voltage, okay? So this is the second relationship. So this means that the drop in the terminal voltage is not only because of the increase in load, but also because of the generated EMF. So the resultant is that the terminal voltage is going to fall at a faster rate as compared to the separately excited generator. So now you can draw the characteristics. So we will draw both the internal and external characteristics on the same graph. So here you have Eg and the terminal voltage, and here you have the armature current. You can take the load current as well, remember, okay? You can write here load current. Now what will be the characteristic? The internal characteristic is going to be like this. It will fall like this, and in fact after reaching a particular maximum value of current, it will start falling down, okay? So this is internal characteristic. External characteristic is going to be further less because of the extra drop in the armature winding, Ia-Ra drop. So this will draw with a different color. So it's going to be like this. This current here you can take as Ia max, and also this is the drop due to Ia-Ra, okay? This is the internal characteristic. That means Eg, variation of Eg with respect to armature current, and this is the external characteristic. So you must be wondering why this curve is taking a plunge here. So what happens is, as the load increases beyond this point, if the load is increasing, then the armature current will not increase anymore. Instead, the voltage will drop off even rapidly. Now one more thing that we did not discuss here in case of shunt generator is the armature reaction. So armature reaction is a bit more complicated in case of shunt generator, that's why we are not discussing here, okay? Now we will move on to the series generator. So here what is going to happen, unlike the separately excited and shunt excited, the initial voltage, that is when the load current is 0, the voltage is also going to be 0. Okay, so why is that the case? We know that in a series generator, the armature current is simply equal to the field current, and this is also equal to the load current. So if there is no load, that means the load current is 0. Then what will happen to field current? Field current is also 0. So then there will be no internally generated voltage, and if there is no EG, then there is not going to be any terminal voltage. So you can write here, at no load, that is when IL is equal to 0, the internal generated voltage is equal to 0 and Vt is also equal to 0. Okay. Now what will happen as the load increases? So as load increases, this means that IL is increasing, and IL is nothing but the armature current. This is also equal to the field current, so this is going to rise. Once field current rises, the field flux is going to rise and the internal generated voltage is also going to rise. But what about the terminal voltage? Vt is equal to Eg minus the drop across the armature, so that is Ra, and also the drop across the field resistance. Okay. Now one thing that you can observe here is, as the load increases, Eg increases. So if Eg is increasing, Vt will also increase, but also Ia is increasing. Okay, but Ia is going to have a reducing effect. Because of increase in Ia, Vt will reduce. Okay, so this point is important here. As Ia increases, this will lead to an increase in the generated voltage, which will lead to an increase in terminal voltage. But also what is happening, as Ia is increasing, the terminal voltage will reduce. So whenever there is a contradictory effect like this, then what will happen? Eventually, whichever effect is bringing more change, that is going to prevail, right? So what happens is, in the initial values of current, the increase in Vt will be dominated. Okay, so the increase in Vt because of increase in Eg. But as current keeps on increasing, then this effect will start dominating and Vt will start reducing. So now you can draw the characteristics. So the internal as well as external characteristics we are going to draw on the same graph, Eg and Vt. Okay. So we will first plot the internal characteristics. So it has to start from 0. As Ia is 0, Eg is also 0. So from here it will go on increasing, and as it reaches saturation, it will stop increasing at a similar rate. Okay. So this is the internal characteristic. What about the external characteristic? This will also start at 0. It will be lesser than Eg because of the drop across armature winding and field winding. Till a certain point it will increase, but after that it is going to start decreasing. Okay, because now the increase in current effect is going to take over. So this is the internal characteristic, that means Eg, and this is the external characteristic, that means Vt. And what about this? This is the drop due to Ia Ra plus Rf, armature winding and field winding drop. Okay, so this is the characteristic, internal and external characteristics for series generator. Next is compound generator. So in compound generator, you're going to have a series winding and a shunt winding, right? So here also there is going to be two effects on the terminal voltage. Okay, what will happen? As Ia increases, then the voltage drop across the armature and field winding, it is going to increase. So this means that the terminal voltage, which is equal to the internal voltage minus the drop, this is going to reduce. Okay, this is one effect. What is the other effect? As Ia increases, the field flux, the series field flux, okay, phi Se, this is going to increase. So if this is increasing, then the total flux, what is total flux? This is equal to the shunt flux plus the flux due to the series winding. So this means that we are first discussing the cumulative compound generator. Okay, cumulative means both the fluxes are additive in nature. Differential we'll discuss later. In differential, these two fluxes will be opposing each other. So we'll have to use a negative sign. Okay. So if total flux is increasing, this means that the generated voltage is also increasing. This means that the terminal voltage, which is equal to once again Eg minus Ia Ra plus Rf, this is going to increase. Okay. So now which effect is more predominant? That is the question. So this depends upon the number of turns in series winding. Okay. So what are the various cases? The first case is, let us say the number of series turns is very small. Okay. So we will take this as NSE. Okay. So NSE is very small. This means very less number of turns are present. In this case, which effect is going to predominate? The first effect is going to predominate. Okay. Because if the number of series turns are less, then the increase in field flux, the effect of increase in field flux will be less. So this entire effect will be less. Okay. So now the drop will predominate. So Vt will have a decreasing effect. So in this case, the terminal voltage Vt will fall with the increase in armature current Ia. Okay. So just like a shunt generator, but if you compare with a shunt generator, the decrease is going to be lesser. Why is that? Because here you have the series winding, which is some effect will be there. It is just that this is not predominating effect. Okay. So if you draw the characteristics, this is going to be, this is the terminal voltage, the armature current, and let us say this is the no load voltage. Okay. From here it is going to keep falling. Okay. So this is the external characteristic when the number of series turns is very less. Okay. And if it is a shunt generator fall will be even more. So this is shunt. And this is called as the undercompounded generator. So you will understand a little later why it is called undercompounded. Now next case is when the number of field turns is moderate. So that means basically the number of turns at which the second effect is predominating. Okay. So in this case, what is going to happen? Initially, effect 2 is going to predominate, and after that, effect 1 will start predominating. Effect 1 will take over. Okay. So that means what is going to happen? Effect 2 predominate means the resultant is an increase in terminal voltage with an increase in armature current. But beyond a certain point, the second effect will start to take over, and in that case Vt will now start falling. So how will the characteristic be? It is going to be first increasing and then it will start to reduce. Okay. Now what is this voltage here? This value is the no load voltage. Okay. So let us take it to be V0. This is the no load voltage. Now you can see that this generator, it is crossing this no load voltage at a particular current value. Okay. So if this current, it occurs at a full load current. That means at full load, the full load voltage is equal to the no load voltage. Okay. So in that case, it is called as the flat compounded generator. Flat compounded generator. Okay. And now if you further increase NSE, then what is going to happen? Here also, initially the effect 2 will predominate. Okay. And effect 1 will take over after a larger period of time. Okay. So that means it is going to be like this, and then it will start reducing a little later as compared to the flat compounded generator. So this is called as over compounded generator. Okay. So basically this, you can take it like a critical value, this flat compounded. All of the generators which are having characteristics above the flat compounded are called over compounded. If it is having below, then it is called under compounded. Okay. So what are these characteristics? Remember, these are the external characteristics. Now what about the internal characteristic? Internal characteristic is nothing but Eg, right? Internal characteristic is Eg versus Ia. Okay, so this is simply going to be a little above. Like for example, if this is the external characteristic, then internal characteristic is going to be slightly above. What will be that value? It is the drop across the field and armature winding, series field and armature winding. So Eg is equal to Vt plus Ia Rse plus Rf. Okay, so that means if you are having a characteristic like this, let us say this is the external characteristic, then internal characteristic is simply going to be like this. And what is this difference? This difference is the drop Ia Ra plus Rse. Okay. Now this is all about the cumulative compound generator. What about differential compound generator? So here it is not going to be much difficult here. Both the effects are going to result in the same thing. Okay. So what was the first effect? As Ia increases, the drop will increase and this will lead to a decrease in the terminal voltage. Vt is equal to Eg minus Ia Ra plus Rse. So this is going to decrease. And what about the second effect? As Ia increases, then the field, series field is going to increase. But here since it is differential, what will happen to the total flux? Phi total is equal to phi sh minus phi se. So why phi sh and this is phi se is negative? Usually the shunt field is going to be more powerful, more strong. Okay. So that's why shunt minus series will be the total flux. So if phi se is increasing, then the total flux, what is going to happen? It is decreasing. And if this is happening, then Eg is reducing and consequently Vt will also reduce. Okay. So it is the same effect. If Ia is increasing, then both these will lead to the same effect, which is the decrease in the terminal voltage. So the characteristic you can draw, this is the terminal voltage and this is the armature current. Now the characteristic, it is going to just simply fall. Okay, fall very drastically. So this is the differential compound generator. In contrast, if you compare with the shunt generator is going to be something like this. Okay, so this is differential compound generator. And once again, if you want to get the internal characteristic, this is the external characteristic, then you simply add the voltage drop across the armature and series winding, then you will get the internal characteristic. Okay. So now we have discussed each of the generator characteristics. Now it is the time for comparison. This is also very important. Okay. So let us take this to be the no load voltage. Okay. So we are talking about the external characteristics here. Okay. So this line represents the no load voltage. Let us take it to be V0. This is no load voltage. Now if you draw various characteristics, okay, shunt and compound you can easily draw because we have just compared both of them. Okay. So let us say this is the under compound generator, then shunt generator is going to be something like this. Okay. What about separately excited generator? It is going to be more than the shunt generator but less than the compound generator. Why? In compound generator you have a additional effect which is reducing the fall in the terminal voltage. Okay. So you can write down here, this is over compounded generator, this is the separately excited generator, and this is shunt generator. Now what about the flat compound? Here you have to draw the full load value. This is the full load value. Then flat compound, first initially it will rise above the no load voltage, then at full load it will reach the exact no load voltage. So this is flat, or it is also called as level compounded generator. And next, over compounded generator will be like this. What is left out now? Series and differential. So differential, anyways we know it will just fall very rapidly. Okay, so this is differential. And what about series? Series is also very different from the other ones because it is going to start from 0. Okay, so it will go something like this. Okay, so this is the series generator characteristic. So this is the comparison of various generators which is important. You have to remember.